So water and acid base balance. When you're talking about acids and bases, we know by definition an acid is anything that can donate a proton, and a base is a proton acceptor. That is just one form of a definition for an acid and base because there are three definitions according to Bronsted, Lowry, Arrhenius, and Lewis. But that's one of the most important ones that we give. Or we can say a base is an acid is any compound that will increase the concentration of hydrogen in solution, while a base will be increasing the concentration of hydroxide in solution. Now, there are two terms that we need to differentiate when we're talking about acids and bases: ionization and dissociation. If we say a compound has been ionized, it means that that compound has either lost or gained electrons and it has ended up forming an ion. For example, you know the way sodium is sodium metal. If it loses to one electron, it becomes sodium ion. That is ionization. But dissociation is a compound being ionic after it reacts or dissolves in water. So for both ionization and dissociation, the compounds are becoming ions. But ionization is where there is loss of gain of electrons. Dissociation is dissolving in water and then a compound ends up having ions. So that's the difference between the two. Please take note because those are exam questions there. So a compound dissociation does happen in water as we have said. So what is going to happen is that sometimes water can react with its own self. That's actually known as auto-ionization. Auto means self. Auto-ionization of water. So water can ionize itself. It can make another water molecule break. For example, you can see these two water molecules. What will happen is that one of these water molecules is going to donate an hydrogen to the other water molecule. So the other water molecule has now three hydrogens, so it becomes an hydronium ion H3O plus. And then the other one has remained with an OH, which is hydroxide ion. So what happens is that a molecule, as we've said, that has got an extra proton, that is the one that was acting as a base, isn't it? Because according to the definition of an acid under the base, a base is a proton acceptor, an acid is a proton donor. So that is how water can end up ionizing. But in solution, if you find the concentration of hydronium, it is the same as the concentration of hydrogen ion because they are both positively charged. So that's the same when you are finding the pH. pH you can find as pH is equal to a negative log of the concentration of hydrogen or the negative log of the concentration of hydronium because it's the same. So you can have two water molecules, one losing an hydrogen to the other one to form hydronium. The other one remains as hydroxide, or just the same water molecule can simply break and hydrogen leaves. So I've got hydrogen and hydroxide. That's why we say the concentration of hydrogen is the same as the concentration of hydronium. This is now known as auto-ionization. Water is breaking itself. And what happens that if there is a change in the concentration of hydrogen and hydroxide, that changes the pH of a solution. And you know, some enzymes in the body work specifically in a given pH. So it will really affect the biochemistry of the cell. Bio just means life. So the way our cells will be able to function are going to be really affected by the concentration of hydrogen and hydroxide. Why? Because there's a change in pH that is happening. Because for pure water, the concentration of hydrogen and the concentration of hydroxide is actually the same. If you calculate the pH, it's going to give you a pH of 7. So you have got some compounds that you can add to a solution, and then it will be able to change the concentration of the hydrogen or the hydroxide. So such We call them acids and bases. And for you to determine how acidic or how basic a compound is, you can use a pH scale, which is running from 1 up to 14, with numbers below 7 being acidic, above 7 being basic, and 7 being neutral. So, what is pH by definition? So, pH is just a measure of how acidic or basic a solution is. And how you find pH, as we said, is given by negative log of the concentration of hydrogen, or negative log of the concentration of hydronium, because we said these are the same. And for pure water at 25 degrees, the pH is supposed to be 7. So if we say a compound has got low pH, it means that you don't have a lot of hydrogen ions in solution. Because if you have got a lot of hydrogen ions, then such a compound has got a very acidic pH, meaning it's going to have a, let me say this again, a compound that has got a low pH. When we say low, we are referring to a pH scale from 1 up to 14. Let's say you have got a pH of 2 and a pH of 4. So a pH of 2 is very low. And a low pH means that the compound is very, very acidic. The meaning of that is that you have got a lot of hydrogens. But a high pH means that the pH is little acidic and more basic. So you have got little hydrogen, probably you have got more hydroxide. Okay. And for our body, the fluids we find in the body, their pH range from 6 to 8. Actually, blood, the pH is 7.35 to 7.45. So that's a normal pH between 6 and 8. That is slightly like neutral. So we have got two terms we need to know: strong acid and base, and then concentrated acid and base. If you hear the word strong, it refers to the ability to dissociate. It's different from the word concentrated. Concentration tells you of how many ions you have got dissolved in water. So a strong acid or a strong base is one that can completely disassociate in solution. Examples of strong acids that we can mention is hydrochloric acid, sulfuric acid, those compounds. But a weak acid, for example, acetate, and a weak base like ammonia can only partially ionize, meaning that as they are breaking into their constituent ions, they will not do it fully. And so what you see is that when you're writing an equation for acetate, you are going to write an arrow going forward and an arrow going behind. Why? Because those are not going to fully disassociate. The strength of an acid or base is going to depend on how much it disassociates. Okay, so compounds that disassociate more, we say they are stronger acids or bases, and those that do it less, they are weaker. And if you want to compare the strength of acids, you can look at their acid dissociation constant, which is known as Ka. So the acid dissociation constant Ka is a measure of the strength of an acid in solution. If you have got a large Ka, it means that that acid can dissociate more, so it is a stronger acid. Now Ka is a very small number, and so instead of us writing Ka, we are going to be using pKa. So every time you put a p in front of a number, for example, if you have got x, you put p, it becomes px. It means that it's going to be negative log of x. If you have got m, you say pm, it is going to be negative log of m. If you have got h, you say ph is going to be negative log of h. If you have got ka, so if you say pka is going to be negative log of ka. So pka is going to be a much convenient way of expressing the concentration of hydrogen ions. But because pKa is negative log of Ka, what happens is that if Ka is very high, pKa is going to be very low. And we said that when Ka is very high, that means that you have got a strong acid. So meaning that for a strong acid, pKa should be very small. So if they give you two acids, one has got a pKa of 4.7, one with a pKa of 3.8. The one with a pKa of 3.8 is actually stronger than the one with a pH of 4, the pKa of 4.7. So you can try to work out this example. Acetic acid is a weak acid with a K of 1.8 times 10 to the 5. We want to calculate the pKa. So all you do is negative log of 1.8 times 10 to the 5. And when you want to find the pH and the pK of a solution, this can actually be related by what we call the Anderson-Hasselbalch equation. The Anderson, this is one equation that you wrote in chemistry. Anderson-Hasselbalch equation is pH is equal to pKa plus log the concentration of the conjugate base over the weak acid. So always start with the base on top over the acid. Please don't forget the equation because they can give you some numbers and then ask you to calculate. I don't want to concentrate on the equation itself because this is something that you just did last year. Okay. Please take note that you use this equation when you have got a weak acid and its conjugate base. Not a strong acid, but weak acid and its conjugate base. So for example, you can see this question, calculate the pH of a buffer solution made from 0.2 molar of this acid. How do I tell that it's an acid? Because there's an hydrogen. And 0.50 molar of this guy, you can see it is negatively charged. It means that you have lost an hydrogen. So if you have got a substance that is negatively charged, that is a conjugate base. The acid has got an hydrogen. And then we've been told that the pKa is 4.7. So all you do is pH is equal to pKa, which is 4.7, plus log the concentration of the base, that is 0.5, over the concentration of the acid, that is 0.2. Punch that on the calculator to give you the answer. Same way with this one, you can also work it out. Another important concept that you need to understand when you're talking about acids and bases is what we call a buffer. The reason as to why we have got buffers in our body is to help us to maintain a constant internal environment. As we said earlier, remember we said that in our bodies we have got enzymes, and these enzymes work in a specific range of pH. Let's say you have got enzyme A, its optimum pH is 7.05. What happens that any slight change in pH will make this enzyme to stop working. So what buffers do is that even when you, because some medicines that we take, some foods that we take are a bit different in pH. So buffers are going to be working in such a way that when you have got a change in pH, they are going to react with that change so that the pH is maintained constant. That's a basic function of buffers. Okay. So what happens for buffers is that they are going to have both the acid component and the basic component. If you put acid, the basic component of the buffer will react. If you put base, the acidic component of the buffer will be able to react. And in our bodies, we have got what we call physiological buffers. You'll be doing physiology, right? Physiology means normal. So we have got buffers which normally maintain our pH constant. Three important ones. We have got bicarbonate buffers, phosphate buffers, and protein buffers. And what happens is that actually the buffer systems are going to pH, internal pH, which is provided by the buffers, is going to also be part of the first line of defense against changes in pH. What happens is this: just like we have got what we call the immune system. Hope you learned something in immunology. What the immune system does is that if something is entering our body that is foreign, the immune system is going to defend us. That is the same one with pH, these buffers. If there's any change in pH, the buffers will come in to maintain the pH constant. So it is actually part of the immune system. Okay. And when you look at the cytoplasm, cytoplasmic fluid, like inside our cells, the cytoplasm, we have got proteins, organic substrates, inorganic salts. All these guys will be able to resist changes in pH, including ATP. It also is going to act as a buffer. So buffers are biologically important if the pH value of blood remains in the either the alkaline or acidic form. Okay, because any change that happens can be destructive, because it can prevent the working of some organs, and it can disturb some reactions that happen in our body to help us function properly. So buffers, simply we can say they are there to maintain homeostasis. Homeostasis is maintaining a constant body environment. If you feel cold, the body tries by all means to maintain your temperature so that you feel hot. If you are feeling not okay, maybe tired, the body is trying to maintain you in a nice state. If you see a lion, the body wants you to be able to react so that you come back to a normal state. All those are buffers. And we have said that in our body we have got things like bicarbonate, phosphates. Actually, our red blood cells carry what we call hemoglobin, which is a red pigment that makes red blood cells to be red. It's also a buffer because it carries hydrogen. But the main physiological buffers that we have are the carbonic acid bicarbonate buffer system, phosphate buffer system, and the protein. These three are very important. I want you to know them. Please be free to ask in case you have got a question. So let's start with the carbonic acid bicarbonate buffer system. I want you to understand this well and ask if you are not okay, because you'll find some nice questions that are going to ask you on this. Look at this. Carbonic acid is this compound like this, H2CO3. This is our carbonic acid. But what carbonic acid can do is that this guy can disassociate. Remember, when a compound loses an hydrogen, it becomes a conjugate. So this can disassociate, and what you are going to form is HCO3. When a compound loses an hydrogen, it becomes negatively charged. Okay. This guy can also disassociate again, and then you are going to find C3, and then it will be now 2 minus. But I'm not interested in this. I'm only interested up to here. So this is carbonic acid. We call this as bicarbonate or hydrogen carbonate, bicarbonate. So what happens is this. When you are talking about conjugates of each other, they differ by one hydrogen. You can see this one has got two hydrogens. This one has got only one hydrogen. So they are conjugates of each other. And the one that has got two more hydrogens is always the acid. The other one is a base. So for this system here, as a buffer, we can write it like this. This one, what will happen is that when I add a base to my solution, what will happen is that this is the acid component of this buffer. It will react with that base. And how is it doing that? We are trying by all means to maintain the normal pH. So for example, if I add sodium hydroxide, that's a base, right? Sodium hydroxide. We are saying that the acid component of the buffer is the one that will react. That is the H2CO3. And what is going to happen in this case is that the sodium will react with the bicarbonate to form sodium bicarbonate. Carbonate. And then the hydroxide will react with the hydrogen to form water. So in this case, we have neutralized the base that came. But if we add an acid to our solution, What is going to happen in that case? It is the basic component of the buffer that is going to react. Let's say, for example, I add hydrochloric acid. So it's actually the basic component of the buffer that is the HCO3 minus, or the bicarbonate that will react. And in this case, what is going to happen? The hydrogen is going to react with the, remember, this is positive, this is negative, this is positive, this is the carbonate is negative. So the hydrogen will react with the hydrogen, but not necessarily like that. Instead, what is going to happen is that the hydrogen will simply come and attach there, and then you are going to form the carbonic acid, and then you remain with the chloride ion alone. Now in solutions, normally what you see is that you are not going to see this guy alone as bicarbonate. Instead, why don't you see it like that? Because we don't want to have things that are ions, that the things that are charged. Instead, in solution, what we are going to see is that we are going to use some group 1 elements to attach to them, for example, sodium. So we're going to see sodium in front like that, so it becomes sodium bicarbonate. And the reason why I've got a sodium, sodium is not changing anything. It's just to make sure that that negative sign that is supposed to be here is neutralized. So as a buffer, you will see it given like this. The sodium isn't changing anything there. It is just making sure that that negative sign isn't there. And so what will happen is that when this reaction happens, the sodium also come and attach here, so you form sodium chloride and the bicarbonate. So this is what happens. Okay, and actually in our bodies we form a lot of normal metabolism produces a lot of bases in the body. That is why we need to have a lot of the acid. Okay, so under normal circumstances there's supposed to be more bicarbonate present than carbonic acid. That's under normal circumstances. Why? The bicarbonate is this one and it's the base. That is because normally the body is producing a lot of base. That's under normal circumstances. So I've already described what happens when you add an acid to the buffer and when you add the base. And I've already said that sodium is just there to regulate or to control the ions. It doesn't really affect the reaction. Does this make sense? Is there any question? Okay, hope that's okay. So another thing we need to know is that what happens is that bicarbonate, using the enzyme which is known as carbonic anhydrase, can break into water and carbon dioxide. And what happens that this carbon dioxide can actually go to the lungs and then you can remove it. So the carbonic acid bicarbonate buffer system is also related to the respiratory system. And then we also have got a phosphate buffer. Now for a phosphate buffer, please take note of how it is. I want you to understand this so that it can be easy. What you have is phosphoric acid. Phosphoric acid is like this, H3PO4. So what happens is that this phosphoric acid can dissociate. If it loses one hydrogen, you are now going to have H2PO3. Remember I said that when it loses one hydrogen, what happens? It's supposed to carry a negative sign, isn't it? But we said that we don't want to be having those negatives, so you can simply attach a sodium in front to balance that negative sign. And then this guy again, what can happen is that it can also lose another hydrogen. And what you're going to have is HPO3. Supposed to have a 2 minus. But again, you don't want to put that 2 minus. Instead, balance it with a sodium. But because you have got 2 minus, so put 2 sodiums. So in this buffer, the acid is going to be this one. The base is going to be this one. You can see the acid has got 2 hydrogens. The base has got only 1 hydrogen. Okay, that's how you tell. So you have got sodium dihydrogen phosphate as the acid, and then disodium hydrogen phosphate as the base. So what is going to happen when you bring a salt? Let's say when you bring a base and react, The acid component is the one that will react. So the acid is the sodium dihydrogen phosphate. This will react with any base that you bring in solution. Let's say, for example, sodium hydroxide. What you are going to end up forming is that the this portion here is the one that is negatively charged. Okay, it's supposed to react with the portion that is positively charged on the other molecule, and that is basically the sodium. That's how the reaction is supposed to happen. And opposite, when you bring in a base, I mean an acid, it is this component that is supposed to react. One important thing I want you to take note is that this buffer is the most important buffer in internal fluid. Like, it is found inside the cells, not outside the cells, but inside the cells. Please take note of that. Inside the cells. Look at what's happening here. Okay. So if we react this buffer with an acid, because sometimes they can give you this equation, so you need to know. Can you see this is an acid? So the component of the buffer that is reacting is what? The base. And we said that the base has got two sodiums, it has got only one hydrogen. So I can simply write this like this: HCl, remove the sodium. That will just be HPO4 with a 2 minus. That's the base. So what will happen in this case if the reaction really happens? So if the reaction happens in this case, what happens is that since this is the acid, remember we said that uh, an acid is a proton donor. So this hydrogen is going to be donated. This guy will act as a base, isn't it? So now this guy is going to gain two hydrogens. So it will now be H2PO4, okay, with 1 minus. And then this chlorine is going to remain alone. And it is having a minus. But because earlier on for this guy we add two sodiums, one sodium is going to attach here to do away with this sign. The other sodium is going to attach there to do away with this sign. This is a product that you can see here. That's the same when you react with a base. You have got the base, which is sodium hydroxide. The acid component is the one that will react. Forget about the sodium. That is H2PO4. Because the H2PO4 is the acid, this is the one that will be donating a proton. So one proton will be removed from here and be given to the hydroxide to form water. Okay. And then the sodium will now react with what remained here. So you have got only one sodium, isn't it? What remained here, because we donated one proton, is just one proton and then the PO4. But then what has happened is that this guy here is actually going to be negatively charged. Why? Because the way it was like this, it was negatively charged. If we lost one hydrogen, it would have a negative, two negative charges. But because we have attached the sodium that is positive, one negative charge is neutralized, so we've remained with one negative charge. But had I put the sodium in front here as it is been given, what happens is that you are going to have two sodiums to be able to neutralize even this negative that's there. That's why I've got this product. So this is how these reactions happen in order to neutralize them acting as buffers. And then proteins are also buffers, but these ones are specifically found in plasma. Plasma is the liquid part of blood. Okay. And most buffering capacity of blood will actually come from proteins. And what happens is that red blood cells contain what we call hemoglobin. Hemoglobin can carry hydrogen, they can bind to hydrogen. And this hydrogen is coming from a conversion because carbon dioxide, if we have got too much carbon dioxide in our bodies, it can react with water. And this is going to form hydrogen ions plus bicarbonate. But before we form this, we are actually going to form first carbonic acid and then it will break. This hydrogen cannot be carried by hemoglobin. So hemoglobin also acts as a buffer. Okay. So these are the buffers that you can see. In extracellular fluid, the fluid that is inside the cells. If you have got this as your cell, the fluid found inside the cell is known as intracellular fluid. The fluid found outside the cell is known as extracellular fluid. Part of the extracellular fluid is found in the blood vessels, and we call that as plasma. So the major buffer in extracellular fluid is a bicarbonate buffer. The major buffer inside the cell is the protein and phosphate, especially the phosphate. And then the major buffer in blood, that is of cellular fluid, is going to be the bicarbonate and the hemoglobin. Okay. In urine, you also have ammonia and phosphate. So these are the buffers. So these questions I'm sending you as quiz, you are going to be able to answer them. We see if you are able to answer. We have already covered them. So that is it for this class. Thank you so much.